Welcome, everyone, and today we'll be telling you about one of the most famous and influential mathematics of all time, Carl Friedrich Gauss. This presentation is brought to you by Julian, William, Jack, and Micah.
Great mathematician Carl Friedrich Gauss, regarded as one of the greatest thinkers in all of history, was born into a poor family in 18th century Germany. He showed his talents as a child and despite his family's poverty received an excellent education in the field of mathematics. Gauss was supported by the Duke of his hometown Brunswick to study at Caroline College. At the age of 15, he earned his doctorate at the University of Göttingen. The Duke continued to support Gauss into his 20s. During this time, Gauss published his monumental work, the Disquisitiones Arithmeticae, a book that revolutionized number theory forever. When the Duke of Brunswick died, Gauss could no longer receive his support. He accepted the chair of astronomy position at Göttingen, which he remained in until his death. Though he enjoyed astronomy, he disliked teaching. However, Gauss later came to like his students. Though Gauss was well known and highly successful, he lived a simple life. He married his first wife, Johanna Osthoff, at the age of 28. His first son, Josef, became an army officer. He had a daughter, Wilhelmina, and another son, Louis, who died as an infant. Johanna also died. Gauss remarried the following year. With the second wife, he had two sons named Eugene and Wilhelm, both of whom became businessmen in America. Gauss also had a daughter named Therese, who stayed with him for the rest of his life. When Gauss's mother was old, he took care of her too. Gauss died at the age of 77 in his sleep. While Gauss published plenty of discoveries, he kept most of his work to himself in his diary, which was not discovered until after his death. The wide variety of contributions from Gauss to science and mathematics are too numerous to include in a short video such as this. One cannot study higher level mathematics without encountering various concepts that bear his name. At a young age, Gauss found a long sought-after method of constructing a 17-sided shape known as a heptadecagon, using only a straightedge and compass. Gauss's laws of electricity and magnetism are foundational to engineering and technology. Gauss also discovered the normal distribution, also known as the bell curve, or the Gaussian distribution, which is considered one of the most important statistical distributions ever, being used in a multitude of academic disciplines. Gauss studied the possibility of non-Euclidean geometry long before it was taken seriously by mathematicians. Another notable discovery by Gauss was the dwarf planet Ceres between Mars and Jupiter. Evidence for the dwarf planet Ceres was first found by observations from the Italian astronomer Giuseppe Piazzi through a telescope. However, the planet was nearly lost when Piazzi was unable to track it. Gauss managed to calculate the orbit of Ceres, allowing astronomers to find Ceres once again and confirming its discovery. Poignantly, Gauss was the last person to become an expert in all branches of mathematics. After his death, mathematics became so complex that it is impossible for one person to study all of it with the amount of depth that Gauss did.
When Gauss was 7 years old, his elementary school teacher gave his class the assignment of summing every integer from 1 to 100. The teacher's aim and expectation was that this would keep the kids quiet for about half an hour, but Gauss almost immediately produced the correct answer of 5050. You may have heard a similar problem or maybe seen the solution to this, but Gauss was the one who first came up with it. What Gauss did was not add up every individual number in his head, but instead he noticed you can add the integers in pairs, 1 to 100, 2 to 99, 3 to 98, so on and so forth, with each pair summing to 101. There are 50 of these pairs, and the only math Gauss had to do was to multiply the sum of 101 to the 50 pairs of numbers, which resulted in that correct answer of 5050. Moving on to spiritual beliefs, Gauss was a member of the Lutheran Church, which is a branch of Protestantism, as you can see circled red here, which is also similar to Quakerism, which was founded by our one and only George Fox, as you can see circled in blue. While Gauss was a member of the Lutheran Church, he did not go to church often, but Gauss strongly upheld religious tolerance, believing that one is not justified in disturbing another's religious belief, in which they find consolation for earthly sorrows in times of trouble. There are also two famous quotes by Gauss related to his faith and religion. I succeeded, not on account of my hard efforts, but by the grace of the Lord, and God arithmetizes. As Will previously mentioned, the number of proofs and ideas Gauss brought to the world of mathematics is too much to include in this short video. For now, we'll be focusing on the Gaussian integral, which is the integral of negative infinity to positive infinity of e to the power of negative x squared, which is equal to the square root of phi. I'll quickly show you the reasoning behind this and the proof of it as well. Both the reasoning And the proof make use of the polar coordinate plane to solve the integral, which you'll see is where and how we get pi. The first part of the reasoning takes our difficult integral and squares it. When and setting x equal to r, we can spread out the square to get two separate integrals, which you can then combine to form a double integral, while also adding the exponents of e in each integral since they have a similar base. Now you can notice that we have in the equation x squared plus y squared an integral, and from geometry, we know that this is equivalent to r squared. Once you switch to r squared, the integral is now in terms of r and theta, and when converting a double integral from a Cartesian plane to a polar coordinate plane, you must multiply by r. The outside integral gets a lower bound of 0 and an upper bound of 2 pi, and the inner integral gets a lower bound of 0 and an upper bound of infinity. Normally, when solving a double integral, you take the inner integral first, and since there is no theta in this equation, we know that the result of the integral will only include theta being multiplied by the current equation. Since the upper bound is 2 pi, we multiply that to our equation, and since the lower bound is 0, it cancels out the subtraction and leaves us with just the 2 pi multiplied by the inner integral. We can rewrite our integral in terms of s, where s is equal to negative r squared. This is done by firstly changing the exponent to be s, since s is equal to our current exponent. You can also therefore infer ds dr. The derivative of s with respect to r is negative 2r, and when you swap that around, you get that dr is equal to negative ds over 2r. Now you can substitute ds over negative 2r and for ds. The r's cancel each other out, and you're left with negative 1/2 and e to the power of s. To get rid of the negative, we use a u substitution, which doesn't change anything aside from the bounds, where the lower bound becomes negative infinity and the upper bound becomes positive infinity. Then you can pull out the 1/2, leaving the outside with just pi, and the integral with e to the s. The integral of e to the s is itself, so the result is pi multiplied by e with the lower and upper bounds. E to the power of 0 is 1, and e to the power of negative infinity is 0. 1 minus 0 is 1, and then you multiply that by pi, which gives us the result of pi. Going back to our original equation, we had squared this difficult integral, to which we found that the result was pi. So taking the square root of both of these results in our Gaussian integral, which equates to the square root of pi. Unfortunately, due to time constraints, I will have to skip this part of the proof, but if you want to look at it, you can totally go ahead, go to Wikipedia. It explains it very well.
Throughout his life, Gauss remained more interested in exploring novel ideas in various fields of mathematics than publishing his conclusions and receiving credit for these ideas. It's unclear whether this was out of a lack of confidence in his work or disinterest in being recognized for it, but he was known at times to be critical of others who published work similar to that which he had completed but had not yet published. Ultimately, he was an individual given insight into how the world around him worked and who wanted to gain understanding more than he wanted to be known for having it.
Thank you for listening to our presentation.